In their mission to grasp the first stars and universes that illuminated the universe, cosmologists are still in obscurity. In any case, drawing nearer to edification, one revelation during a period that is the fantastic inevitable end from remarkable revelations by the James Webb Space Telescope or JWST, the 1 billion time machine that just authoritatively shut its most memorable year of perceptions intended to impression the faint infrared sparkle of the universe's earliest iridescent articles. Webb's vision ventured once more into the initial not many 100 million years after the enormous detonation, permitting it to acquire more and better information about infant worlds than any other office yet assembled. Yet, its corridor of cosmic child pictures has demonstrated more abundant than most scientists dared to dream. Just put, applicant systems in the early universe are springing up in numbers that oppose expectations, with handfuls seen as up to this point, and that makes researchers go ballistic, as Charlotte Bricklayer, an astrophysicist at the College of Copenhagen, said. We truly weren't anticipating this. In the long stretches of time following JWST's discoveries of shockingly mature early systems, scholars and eyewitnesses scrambled to make sense of them. Could the pack of bizarre large and brilliant early universes be illusory, maybe due to defects in the examination of the telescope's underlying perceptions? If certifiable, could they might somehow or another be made sense of by standard cosmological models, or quite possibly, were they the first hints that the universe is more strange and complex than even our boldest speculations had at any point assumed? And the huge bang hypothesis, was it off base? Join us today as we dive deep into how the James Webb Space Telescope broke the universe. Let's get to the highlight, understand the difficulty, and go back to when the universe was believed to have been framed after the huge explosion. The newborn child universe started chilling inside a couple million years. The roiling plasma that occupied space settled down, and electrons, protons, and neutrons joined into atoms, generally impartial hydrogen. Things were peaceful and dim for a time of dubious term known as the infinite dim ages. Then something happened. Most of the material that flew separated after the huge detonation is made of something we can't see called dark matter. It has applied a strong impact over the universe, especially at first. In the standard picture, cold dark matter, a term that implies undetectable or sluggish particles, was flung about the universe aimlessly. In certain areas, its dispersion was denser, and in these regions it started imploding into clusters. Visible matter, meaning molecules, bunched around the clusters of dark matter. As the atoms chilled too, they eventually densified, and the first stars were born. These new sources of radiation re-energized the neutral hydrogen that filled the universe during the alleged age of reionization. Through gravity, larger and more mind-boggling structures developed, building a huge infinite trap of universes. In the interim, everything continued to fly apart. The universe is expanding rapidly. The cosmologist Edwin Hubble sorted out in the 1920s that the universe is expanding, and in the late 1990s, his namesake, the Hubble Space Telescope, found evidence that the development is speeding up. Consider the universe a portion of raisin bread. It starts as a combination of flour and water, yeast, and raisins. When you combine these ingredients, the yeast begins breathing, and the portion starts to rise. The raisins inside it substitute for systems, stretch further apart from each other as the portion expands. The Hubble telescope saw that the portion is rising much quicker. The raisins are flying apart at a rate that defies their gravitational attraction. This speed increase appears to be driven by the shocking energy of room itself, suppose dark energy, which is addressed by the Greek letter lambda. Plug values for cold dark matter, normal matter, and radiation into the situations of Albert Einstein's general hypothesis of relativity, and you get a model of how the universe develops. This lambda cold dark matter or LCDM model matches practically all observations of the universe. One method for testing this image is by checking the exceptionally far-off worlds out. Identical to thinking back so as to the initial not many 100 million years after the gigantic applaud that began it all, the universe was easier then, its development simpler to analyze against predictions. Stargazers initially attempted to see the earliest designs of the universe utilizing the Hubble telescope in 1995. Over 10 days, Hubble caught 342 openings of an unfilled-looking patch of space in the enormous scoop. Stargazers were amazed by the overflow stowing away in the inky dull. Hubble could see thousands of worlds at different distances and transformative stages, extending back to a whole lot sooner times than anybody anticipated. Hubble would proceed to discover some truly far-off worlds. In 2016, cosmologists viewed as its generally far-off one, called GNZ11, a weak smirch that they dated to around 400 million years later, the huge explosion. This was shockingly early for a universe. However, it didn't cast out on the LCDM model, in part because the world is small with only 1% of the smoothwave's mass, and in part because it stood alone. Stargazers required a more powerful telescope to see whether GNZ11 was an oddity or part of a larger population of mysterious early cosmic systems, which could assist with determining if we are feeling the loss of a fundamental piece of the LCDM formula. That's why the James Webb Space Telescope, or JWST, was conceived. Prestigious as the largest, most powerful observatory ever sent off from Earth, the JWST was built to alter how we might interpret the universe. Positioned 1.5 million kilometers away from natural impedance and chilled near absolute zero by its tennis court-sized sunshade, the telescope carries a giant segmented mirror and beautifully sensitive instruments that were designed to reveal details of vast dawn up until now never noticed. And that contribution was kept as the first discoveries were obtained within weeks after JWST full operations were beyond cosmologists' most outlandish dreams. It has seen worlds extremely close to the earliest days of recorded history, tested the atmospheres of exoplanets in exceptional detail, and provided stunning new views of universes in our planetary system. But it's just getting everything rolling, as Webb's vision steps once again into the initial few hundred million years after the huge explosion, allowing it to obtain more and better information about infant galaxies than any other facility yet built. In question is nothing less than our true understanding of how the structured universe we know emerged from early-stage chaos. Webb's early disclosures could rewrite the opening chapters of cosmic history, which concerned not only ages and faraway universes but also our own existence here in the familiar smooth manner. As JWST scientist Mark McCaffer, a senior advisor for space and exploration at the European Space Agency, said, "You build these machines not to confirm the worldview but to break it. You just don't know how they will break. A form of the Doppler effect to measure the distances of objects. This is similar to figuring out the location of an ambulance based on an alarm. The alarm sounds higher in pitch as it draws nearer and then lower as it retreats. The farther away a galaxy is, the faster it moves away from us, as its light stretches to longer frequencies and appears redder. The extent of this redshift is expressed as z, where a given value of z lets you know how long an object's light probably traveled to reach us." One of the first papers on JWST data came from Naidu, the MIT cosmologist, and his colleagues, whose search algorithm flagged a galaxy that appeared mysteriously bright and untouchably distant. Naidu named it Glass Z13, indicating its apparent distance at a redshift of 13 further away than anything seen before. The galaxy's redshift was later changed down to 12.4, and it was renamed Glass Z12. Other astronomers working on different sets of JWST observations were reporting redshift values from 11 to 20, including one galaxy called CHEER 1749 or CR2Z71, whose light appears to have left at 13.7 billion years ago. Just 220 million years after the Big Bang, barely an eye squint after the beginning of cosmic time itself. These putative detections suggested that the ideal story known as LCDM may be incomplete in some way. Universes became colossal immediately in the early universe. "You don't anticipate seeing gigantic universes," said Chris Lovell, an astrophysicist at the College of Portsmouth in Britain. Indeed, in a review published in November, researchers analyzed computer simulations of universes governed by the LCDM model and observed that JWST's early bright galaxies were arranged by size heavier than the ones that formed simultaneously in the simulations. Some astronomers and news sources claimed that JWST was breaking cosmology, but not everyone was convinced. One issue is that LCDM predictions aren't always clear. While dark matter and dark energy are straightforward, visible matter has complex interactions and ways of behaving, and no one knows exactly what happened in the first years after the Big Bang. Those excited early times should be approximated in computer simulations. The other issue is that it's hard to tell exactly how far away universes actually are. In the months following the first papers, the periods of some of the supposed high redshift worlds have been reevaluated. Some were downgraded to later phases of cosmic evolution due to the updated telescope adjustments. CHEER 1749, for example, is found in a region of the sky containing a cluster of galaxies whose light was emitted 12.4 billion years ago, And Naidu says it's possible the galaxy is part of this cluster, a closer interloper that may be filled with dust that causes it to appear more redshifted than it actually is. According to Naidu, Cheer 1749 is unusual. Regardless of how far away it would be another kind of universe that we didn't know about, a very low-mass, tiny galaxy that has somehow grown a lot of dust in it, which is something we generally don't expect for the very distant universes. For the extremely far-off universes, everyone knew that the most definitive distance estimates would require JWST's most powerful capability. JWST not only notices starlight through photometry, or measuring brightness, but also through spectroscopy, or measuring a light's frequencies. If a photometric observation is like a picture of a face in a crowd, then a spectroscopic observation is like a DNA test that can tell a person's family ancestry. Naidu and others who saw as large early galaxies measured redshift using brightness-derived estimates, essentially looking at faces in the crowd using a good camera. That method is far from airtight. At a January meeting of the American Astronomical Society, astronomers jested that maybe half of the early galaxies seen with photometry alone will turn out to at most be measured. Yet in early December, astronomers announced that they had combined the two methods for 4 galaxies. The JWST's Advanced Deep Extragalactic Survey, or JADE's team, searched for galaxies whose infrared light spectrum suddenly cuts off at a critical frequency known as the Lyman break. This break occurs because hydrogen floating in the space between galaxies absorbs light due to the ongoing expansion of the universe, the ever-rising raisin portion. The glow of distant galaxies is shifted, so the frequency at that sudden break moves too. When a galaxy's light appears to drop off at longer frequencies, it is more distant. JADE's identified spectra with red shifts up to 13.2, meaning the galaxy's light was emitted 13.2 billion years ago. As soon as the data was downloaded, JADE scientists began freaking out in a communal clearance bunch. According to Kevin Hain, an astronomer at the University of Arizona, he said it was like, "Oh wow, we did it, we did it, we did it." These spectra are just the start of the thought process will be space science. As Robert Kirchner, JADE stargazer at the University of California, Santa Cruz, says, the findings show that the early universe changed rapidly in its first billion years, with the galaxies evolving 10 times faster than they do today. It's like how a hummingbird is a small animal, he said, but its heart beats so rapidly that it's living kind of a different life than other animals. The heartbeat of these galaxies is going on a much more quick timescale than something the size of the Smooth Way. But were their hearts beating too fast for LCDM to figure out? As astronomers and the public marveled at JWST images, scientists began working behind the scenes to determine if the galaxies flickering in our view actually rely on LCDM or just help to secure the numbers we should plug into its equations. One significant yet poorly recognized number concerns the masses of the earliest galaxies. Cosmologists attempt to determine their masses to tell whether they match LCDM predictions. The mass of a galaxy is derived from its brightness, but Megan Donahue, an astrophysicist at Michigan State University, states that at best, the relationship between mass and brightness is a fair deduction based on assumptions gathered from known stars and well-studied galaxies. One vital assumption is that stars generally form within a certain statistical range of masses, called the initial mass function, or IMF. This IMF boundary is critical for inferring a galaxy's mass from measurements of its brightness because hot, blue, heavy stars produce more light, while most of a galaxy's mass is typically locked in cool, red, small stars. But it's possible that the IMF was different in the early universe. If so, JWST's early galaxies might not be as heavy as their brightness suggests. They may be bright, but light. This possibility causes headaches because changing this fundamental input to the LCDM model could give you almost any answer you want, Lovell says. Some astronomers consider tinkering with the IMF the location of the devil. If we don't grasp the initial mass function, then figuring out galaxies at high redshift is really a challenge, said Wendy Freeman, astrophysicist at the University of Chicago. Her team is working on observations and programmatic insights that will help nail down the IMF in different environments. Over the course of the fall, many researchers came to think that changes to the IMF and other factors could be enough to square the very early galaxies lighting upon JWST instruments with LCDM. I believe it's quite likely that we can accommodate these observations within the standard worldview, said Rachel Somerville, an astrophysicist at the Flatiron Institute, which, like Quantum magazine, is funded by the Simons Foundation. Nevertheless, she stated out loud, Whatever we learn, it's about how fast can dark matter halos gather the gas. How fast could we ever make the gas cool off and get dense and make stars? Maybe that happens faster in the early universe, maybe the gas is denser, maybe somehow it is flowing in faster. I think we're still learning about those processes. Somerville also studies the possibility that black holes interfered with the baby universe. Cosmologists have seen a few glowing supermassive black holes at a redshift of 6 or 7, about 1 billion years after the Big Bang. It's hard to imagine how at that point stars could have formed, died, and then collapsed into black holes that ate everything surrounding them and began spewing radiation. But if there are black holes inside the putative early galaxies, that could explain why the galaxies appeared so bright, even if they're not very massive. Somerville said confirmation that LCDM can accommodate at least some of JWST's early galaxies appeared the other day. Christmas astronomers led by Benjamin Keller at the University of Memphis checked a handful of major supercomputer simulations of LCDM galaxies and found that the simulations could produce galaxies as heavy as the 4 that were spectroscopically studied by the JADES team. These 4 are notably smaller and dimmer than other purported early galaxies, such as Glass Z12. In the team's analysis, all the simulations yielded galaxies the size of the JADES findings at a redshift of 10. One simulation could create such galaxies at a redshift of 13 equal to what JADES saw, and 2 others could build the galaxies at an even higher redshift. None of the JADES galaxies was in tension with the prevailing cosmological model. Keller and colleagues posted the preprint server arcs4.org on December 24th, but they fell short on heave to break the winning cosmological model. The JADES galaxies have other outstanding qualities. Their stars seem to be uncontaminated by metals from recently exploded stars, Heinlein says. Their population 3 stars, the eagerly sought-after first generation of stars to ever light, and that they may be contributing to the reionization of the universe. If this is true, JWST has now looked back to the mysterious era when the universe was set on its current course. Despite the big-picture findings, stuck scientists remain in a state of flux, continually testing, analyzing, and rethinking the data provided by the James Webb Space Telescope, JWST. The telescope's exceptional capabilities offer a tantalizing glimpse into the earliest moments of cosmic history. But the complexities of interpreting this data highlight the challenges inherent in unraveling the mysteries of the universe. As researchers delve deeper into the observations yielded by JWST, they face a myriad of questions that defy easy answers. The discrepancies between theoretical models and observational evidence spark debates within the scientific community, driving further investigations and refinements of existing theories. Each new discovery serves as a catalyst for advancement, pushing the boundaries of our understanding and paving new avenues of inquiry. As scientists continue to sift through the wealth of data provided by JWST, they do so with a sense of humility and reverence for the vastness of the universe. Each observation offers a fleeting glimpse into the cosmic tapestry, inviting us to contemplate our place within the grand design of existence. And while the journey toward enlightenment may be fraught with challenges and uncertainties, it is ultimately a journey worth undertaking, an odyssey that promises to expand our horizons and deepen our appreciation for the wonders of the universe. In this ongoing quest for knowledge, collaboration, and interdisciplinary discourse play crucial roles. Scientists from diverse fields come together to share insights, challenge assumptions, and collectively push the boundaries of knowledge. Through collaborative efforts, researchers can leverage their respective expertise to tackle complex questions and decipher the intricate workings of the universe. Moreover, the significance of JWST extends beyond the realm of pure scientific inquiry. Its discoveries have the potential to inspire future generations, igniting a sense of wonder and curiosity about the universe. By fostering a deeper appreciation for the beauty and complexity of the cosmos, JWST serves as a catalyst for scientific literacy and public engagement. As we navigate the complexities of astronomical exploration, it is essential to maintain a sense of curiosity, humility, and openness. The universe has always been and will continue to be full of surprises, challenging our biases and inviting us to explore new frontiers of knowledge. Ultimately, the journey of discovery fueled by JWST is not just about unraveling the mysteries of the universe. It is about embracing the inherent wonder of exploration and the boundless possibilities that lie ahead.